right, class, today we're starting chapter 6, which is all about rational expressions and functions. Remember, we did chapter 5, chapter 8, and now we're going to go back and finish 6 and 7. So section 6.1 is all about rational expressions and functions. So it's kind of an introduction to them. We're going to learn how to simplify them, determine their domains, multiply, and divide them. So a rational function is defined by a quotient of polynomials that has the form f of x equals p of x over q of x, where q of x doesn't equal 0, right? And we can't have our denominator equal 0 because that would mean we were dividing by 0. So the domain of rational functions is all real numbers except those that would make q of x, our denominator, equal to 0. So what we want to do in order to define the domain is this. I'm going to first factor the denominator. What word is this? I want to factor the denominator. I'm going to set my denominator equal to 0 and solve for the points not included in the domain. I can then write our domain in set or interval notation. I'm going to do both in order to make sure you guys know how to do both. On the homework, it will tell you specifically whether to use set or interval notation, and on an exam, I might say use both or one or the other, so just be sure you have both of those in your toolkit. So if I have f of x equals 3 over 7x minus 14, I'm going to factor my denominator, so 7x minus 14 becomes x. 7 times x minus 2, and I set this equal to 0. So I have 7 equals 0, so we ignore that, and I've got x minus 2 equals 0, which I can solve for. So I add 2 to both sides, and I get that x equals 2. What that means is if I was to substitute 2 into 7x minus 14, I would have a denominator equal to 0, which is not good. So let's write this in set notation first. So this would be x such that, that's what this vertical bar means, and I think I've said that before, such that x doesn't equal 2. Or I can write this in interval notation. Kind of remember when we were working with a number line, the only point I'm skipping over is 2. So I go from negative infinity to 2, and then 2 to positive infinity. All right, let's change colors and look at this next example. I've got f of x equals 3 plus x over x squared minus 4x plus 3. So the first thing I need to do is factor this denominator. So I think, okay, what are some factors of AC, which is 3, that add up to b, which is negative 4, and that's going to be negative 1 and negative 3. Now that I have fully factored, I set this equal to 0, and we use the zero factor property to pull this apart. So I get x equals 1 and x equals 3. Now I have two x values that are excluded from my domain. Oops. In set notation, that's going to be x such that x doesn't equal 1, 3. We just put both those numbers in there. But for interval notation, I want us to quick sketch a number line and think about what we're doing. So what we're doing is we're skipping over 1 and we're skipping over 3, but x could be anything in between. So if I was going to write this in interval notation, it would go from negative infinity to 1, union with this area right here in the middle, 1 to 3, union again with this part right here to the right of 3 to positive infinity. Here are some special cases of our domains. So here I have f of x equals 8x plus 3 over 3. What's special about this is if I set my denominator equal to 0, I get a false statement, right? It's important for us to see that because my denominator can never equal 0, my domain is all real numbers. So it goes from negative infinity to positive infinity. The same thing is true about this second problem here, okay? So if I have 2 over x squared plus 4, what's really unique is if I set this equal to 0, I get x squared equals negative 4, and I can't take the square root of a negative right now, right? We live in real number land. So this is never going to be negative. You can see that be the case. If I had x as negative 1, negative 1 squared becomes a positive 1 plus 4, that's 5. If I had x was 0, 0 squared plus 4 is 4, 1 squared plus 4 is 5. So this is always positive as well. Okay, so its domain would be negative infinity to positive infinity. So the first thing I want to talk about is how to simplify rational expressions. They need to be simplified. So what we're going to do first is factor out the denominator, factor the numerator, factor the denominator, and find their greatest common factor. We're then going to eliminate that greatest common factor in order to divide these polynomials. So if I have x squared minus 3x minus 18, I say what are the factors of AC that add up to b, and that's going to be negative 6 and 3, so I have x minus 6, x plus 3. I then have x squared plus 7x plus 12, and I think, okay, what are the factors of AC, which is 12, that add up to b, which is 7? In this case, it's 3 and 4. So I'm going to have x plus 3, x plus 4. We can see that the factor these two have in common is x plus 3, so those are going to cancel, and I'm left with x minus 6 over x minus 4. So we're just eliminating the common factors. So let's go ahead and simplify the following. I've got y squared minus 4 over 2y minus 4. That's going to give me y plus 2, there's y minus 2 because this is a difference of perfect squares, over, in the denominator I'm going to pull out the greatest common factor, so that's going to be 2 times y minus 2. The greatest common factor that both of these have in common, meaning the numerator and the denominator, is y minus 2, so I'm left with y plus 2 over 2. So let's go ahead and simplify x cubed minus 27 over x minus 3. This numerator is a perfect cube, so it's going to factor into x minus 3 times x squared plus 3x minus 9 plus 9. And if you aren't sure how I did this, you need to go back and review chapter 5. Chapter 5 is where we went over all the factoring rules, and the videos have all been posted. Over x minus 3. As we can see, x minus 3 cancels, and I'm left with the 2-degree equation, second-degree equation, x squared plus 3x plus 9. This next, I have PR plus QR plus PS plus QS over PR minus QR. So I'm going to go ahead and factor this numerator by grouping, and the denominator as well. The greatest common factor of PR and QR is R. The greatest common factor of PS and QS is S, all over R times P minus Q. So I have R plus S times P plus Q over R times P minus Q. As you can see, nothing simplifies here. We should kind of feel like, oh man, I want to simplify these two, but we can't because one's plus and one's minus, so that's not the same greatest common factor, so they will not divide out. What I want to show you is this. So if I have m minus 3 over 3 minus m, first thing first, we should realize, we want our variable first, so I'm going to rewrite the denominator as negative m plus 3. Then we should also notice that we don't like negative leading coefficients. So I'm going to pull out that negative. So I've got negative m minus 3. My m minus 3's cancel, so I've got 1 over negative 1, which is just negative 1. Next, I have r squared minus 16 over 4 minus r. Again, this is another example where we have our constant before our variable and we don't like that. So I'm going to go ahead and factor my numerator to be r minus 4 times r plus 4 because it's a difference of squares. Then I have negative r plus 4 in my denominator. I can pull out a negative. So I've got r minus 4 times r plus 4. My r minus 4's cancel, so I have r plus 4 divided by negative 1. And we might be tempted to write that as negative r minus 4, but remember we don't like negative leading coefficients, so we're going to pull that negative back out and have negative r plus 4 as our final answer. The last thing I want to talk about is multiplying rational expressions. So if we're multiplying rational expressions, what we're going to do is we're going to multiply the numerators, multiply the denominators after we factor them. So this is much like fractions where we multiply the numerators and multiply the denominators. 1 times 3 gives me 3, 2 times 4 gives me 8. But the first thing we have to do is factor. Then we're going to simplify our fractions if we can. We want to multiply the numerators and denominators and leave them in factored form. This is going to be easier for us to work with. And then we can simplify by dividing out the common factors if necessary. So I have 5 times x minus 1 over x times 3x squared over 10x minus 10. That's 10 times x minus 1. Now I just multiply across, and we can go ahead and multiply together the constants. So 5 times 3x squared gives me 15x squared times x minus 1 over 10 times x gives me 10x times x minus 1. Our x minus 1's cancel, and I have 15x squared over 10x. Well, we learned our rules for simplifying exponents in chapter 4. So x squared over x is going to leave me with an x in the numerator. And 15 and 10, I can both pull out a factor of 5, so I'm going to have 3 halves. So I get 3x over 2 is my final answer. The last thing we're going to cover in section 6.1 is dividing rational expressions. They're just like fractions, keep, change, flip. So if I have 1/2 divided by 3/4, I keep the first fraction the same, I change from division to multiplication, and I flip the second fraction. So 3/4 becomes 4/3. 1 times 4 is 4, 2 times 3 is 6. This simplifies to 2/3. We're going to do the same thing when it comes to using rational expressions, but the first thing I need to do is factor my numerators and denominators, simplify each of those as much as much as I can by eliminating the common factors. Then we're going to keep the first function the same, change from division to multiplication, and flip the second fraction. So let's go ahead and factor our numerators and denominators. So 8k minus 16, that becomes 8 times k minus 2 over 3k, divided by 3k minus 6, that's 3 times k minus 2 over 4k squared. I keep my first fraction the same. I change from division to multiplication, and I flip my second fraction. So I get 4k squared over 3k minus 2. I can then go ahead and multiply. 8 times 4k squared, that becomes 32k squared times k minus 2. 3k times 3 is 9k times k minus 2. My k minus 2's cancel. That leaves me 32k squared over 9k. We learned how to simplify exponential expressions before. So I have 32k over 9, and I can't simplify this any further.